of the boost converter there is reduced, or at sometimes like the need of the boost converter is eliminated altogether, right? So I'll be like taking up the fundamental working of this kind of converters, but in general, multi-level inverters are being commercialized and they are being employed to a number of applications, basically motor drives applications, renewable energy applications, battery energy storage systems, and now we have like electric vehicle traction systems as well as charging systems. To both multi-level inverters are being used. Additionally, like high power density apparatus also, which is going to play a major role in uh, power systems for like data storage applications. Like for data centers, we need renewable energy, and uh, since the cost of real estate is too much, like high power density apparatus is required. So multi-level inverters are playing an important role to come up with high power density apparatus for such applications where like renewable energy is being employed for data centers and uh, places like that. Fundamental advantages of multi-level inverters, like I'll take up only a few minutes on this. Like the basic advantage is that the requirement of switches, their voltage rating is very less as compared to the overall output that is obtained from a multi-level inverter. So what we do is that we use low voltage switches, and we get a waveform with much higher voltage. So this is the fundamental advantage uh, of multi-level inverters. Now this is a hardware-based advantage, right? In addition to this hardware-based advantage, we also get certain advantages in terms of the output waveform. The output waveform, since it is stepped in nature, it has better quality. The harmonic profile is much better, and the dV by dt stress on the AC load is highly reduced. And now this is important, especially for renewable energy applications where we are using a filter before connecting the energy system to the grid. So the life of filter is greatly enhanced if the dV by dt stress on it due to the inverter itself is less. Similarly, this dV by dt stress on the power switches is also greatly reduced. So these are some of the advantages due to which like a number of topologies now are being used for renewable energy application. And I believe like today's special session, which will be given by Dr. Vahedi, like he is a pioneer in this field where he has commercialized his topologies for PV inverters. So I am basically looking forward to that session, and I hope like all of you also will be attending that session with great attention. So these are some of the advantages, and the topologies which are considered classical or conventional are diode clamped, flying capacitors, and cascaded H-bridge converter. In addition, like there are certain topologies which have gained a lot of prominence uh, in the past like 10 years. Three of those topologies are modular multi-level converter. This is also being used in renewable energy applications in addition to HVDC application for which like they were mainly conceptualized. Similarly, T-type inverter and active neutral point converters, both of them are also being employed for renewable energy applications. So this is a brief introduction on the applications, the advantages and topologies of multi-level inverters. Now, since we have numerous topologies, like a question may arise like why do we need more topologies on it, right? So there are certain limitations of these conventional topologies. The very first one is that for a high resolution waveform, that is if the number of levels is large, then you need a lot of power switches for the structure. Now each power switch has its own gate driving unit, its own protection unit, and most of the times its own heat sink also. So for every increment in the number of power switches, the overall volume of the system increases because you need gate drivers, protection units, and heat sinks. Therefore, it is highly desirable that we get a high resolution waveform with low number of power switches. So this is an important concern due to which numerous new topologies are getting evolved. Now this is from our perspective today, like these two are the main limitations of the conventional MLIs. Now, one important limitation is that they operate with a unity voltage gain. So if I have an input voltage of, let us say, equal to VDC, then the peak value of the output will also be VDC. So there is no inherent voltage boosting. So what happens is, like I have a source here, a renewable energy source, and I have the load here, which may be the grid or a standalone AC load. In between, we do need an inverter because the load is mostly AC. But this source voltage, since it is very less, we also need a boosting stage here. Right, so the overall system typically looks like this. And of course, you have a filter here. Now, most of the inverters that are employed, they operate with unity voltage gain. They do not provide any inherent voltage boost. So this is an important limitation of the conventional MLIs. The class of inverters that we are going to discuss today, they provide an inherent voltage boost. So what happens is that the size of this boost converter gets reduced because some amount of boosting is provided by the inverter itself. And in some cases, I'll discuss one case where the boost provided by the inverter is so good that you do not need this boost converter at all. Another important limitation is in terms of balancing of capacitor voltages in the conventional inverters, multi-level inverters. Now, especially for three-phase systems, like if you have a lot of capacitors there, then balancing the voltages mandatorily requires a closed loop system. A number of sensors will be involved and the overall system becomes very complex. Especially if you increase the number of levels, then the number of capacitors also increases. And the complexity is so much that people say that multi-level inverters should not be employed beyond 5 levels. But for switched capacitors based inverters, we see that the balancing of capacitors is natural. You don't have to implement any closed loop scheme for that. So these are the two fundamental advantages of switched capacitor topologies. There are certain disadvantages also, which will be revealed as we discuss the working of these structures. So to start with, like I'll take example of a very simple inverter, and I'll show like how boosting, a natural boosting in the inverter itself is obtained, right? So I have shown a structure here. Here this load is an AC load, and I have a DC source here. In order to boost the voltage, like I am using two capacitors, C1 and C2. So I'll be showing you some of the working states of this topology, and we can see like how a voltage gain is achieved in like simultaneously with a multi-level output, right? So for example, in this state, what we are doing is we are turning on S2 and S4 simultaneously along with this bidirectional switch. So if you see the load, like if we apply KVL here, we see that the output voltage is equal to the input voltage, V0 is equal to VDC. And at the same time, if you look at this path, you see that this capacitor C2 is in parallel with the DC source VDC. So what happens is that this capacitor C2 gets charged to a voltage which is equal to VDC. So here we have two paths. One path is charging the capacitor to a voltage VDC. The other path, sorry, the other path, like it supplies a voltage level to the load, and that level is equal to VDC here. I'm taking another state, and in this state, if you see this time, like we have capacitor C1 in parallel with VDC. Here C1 is in parallel with VDC, and we also see that the load is also connected to VDC. This time the polarity of the voltage is reversed. Here you see that this higher potential, the reference higher potential terminal is connected to the higher potential terminal of the load, Whereas in the second state, this reference higher potential terminal is connected to the lower potential terminal of the source. So we see here that output voltage is equal to minus VDC. Now I have shown one more state here. Here what happens is the input source VDC is not connected to the load, but the load is being supplied by a series connection of C1 and C2. Here we see that C1 and C2 are in series and they are supplying the load. And if we apply KVL here, we see that we have seen, like in the past two states, that C1 was charged to a voltage VDC. C2 was also charged to a voltage VDC. And this total voltage, since C1 and C2 are in series, this is being applied to the load V0. The load. So the output voltage V0 is equal to 2 VDC. If we change the pattern of switching, here you see that the output voltage is minus 2 VDC. And these are the waveforms that we get after simulating this topology. I'll be coming to the like how to control and all, but here my focus is on the topological features. For an input of 100 volts, we see that the output voltage, the peak value of the output voltage is 200. So basically we are achieving a voltage gain of 2, right? We are doubling the voltage, and this kind of approach may decrease the boosting requirements from the DC to DC side there, right? So we get a fairly balanced like voltage profile for the capacitors, and this principle where we see that like the capacitor is coming in parallel with the source and like the load is being supplied with a series connection. This principle is called switched capacitors principle. We are switching the capacitors, we are charging them by bringing them in parallel with the source, and we are discharging them by bringing them in series with one another or in series with the source itself and connecting them to the load. Right. So this principle is called switched capacitor principle, and this principle is applied in many interesting ways to different types of topologies, which I'll discuss. Now, the disadvantage of this kind of approach can be directly like understood from the working principle here itself. Like in here, when I am bringing this DC source and capacitor C1 in parallel, and initially, like let us say this capacitor was completely uncharged, then we see that the amount of current will be large. Large currents will flow when we bring capacitors in parallel with the DC source, right? So this is one of the important limitations of this topology. So this is reflected here. Like for example, here you see this is the load current and peak value is somewhere around like 4.7 or 8 amperes. But the source current goes up to 13 or 12 amperes, right? So now this additional current, the spikes that we are seeing, this is because the capacitors are repeatedly, they are coming in parallel with the source. Still, solutions can be found to this problem. I'll discuss those towards the end of the this discussion. So this is one of the simplest topologies. Now what I'll be giving some more examples. Here we see that the number of levels in the output here, you see 100 is one level, 200 is one level, 0 is one level, minus 100 and minus 200. So number of levels here is 5. And the boosting factor, the gain that we are obtaining from this topology is 2. Right, we are increasing the voltage by a factor of 2 here. So I'll take two approaches here. I'll give example of a topology where the number of levels is drastically increased, and I'll give some examples where the boosting gain is also, the boosting factor is also drastically increased. So we'll see the disadvantages also of both the approaches, and we'll see the advantages. So first, like I'm taking example of a topology which offers 9 levels, which is fairly good. Like for renewable energy applications, normally it is said that 9 to 11 levels are good enough for directly connecting the source to the load, right? You do not need filters. Like if properly modulated, the THD will be less than 5%, and the individual harmonics can also be greatly reduced. So you may not need any filter if the number of levels is 9 or 11, right? So I'm taking an example where we are able to synthesize 9 levels, although the voltage gain remains 2 here, right? So this is the topology. We just need to remember that we charge the capacitors by bringing them in parallel with the source, and simultaneously the load is supplied with multiple levels, right? So here I'm taking an approach where I show the direction of the current also, so that uh, we can appreciate like the role of the switches here. So what I'm doing here is I am considering these are the load terminals A and B, and I'm considering that if A is at higher potential with respect to B, then the voltage is positive, otherwise it is negative. And if the direction of current is from A to B, then I'm considering the current to be positive. So I'll be showing the states with uh, both directions of the current, assuming that the load is inductive in nature. So here you see that like I have shown here two states. In each state, like you find two kinds of paths. This path, which is in blue color, and another path, which is in red. The blue color path is basically for the load, and the red colored path is basically for charging of capacitors, right? So simultaneously, both things are being done here. So if you follow this path, blue path, and if you apply KVL here, you see that uh, the voltage here is 0 volts. I'll explain how. But more importantly, like I have a path of which is being used to charge the capacitors. Now, uh, like I had discussed about what happens like when I have a capacitor in parallel with the source, right? The charging currents will be very large. What I'm doing here is I am using two capacitors now, which are in parallel with the source. So this is an approach because the ESRs of the capacitors will is going to, now we are using two capacitors, so the ESRs will be playing a role in limiting the charging current. So this approach is beneficial like in limiting those currents. So what is happening here is when the capacitors they are getting charged, like a series combination of these capacitors is in parallel with V in, right? So this is the DC input, and these are the capacitors C1 and C2. So this overall voltage to which this combination gets charged to is V in. So we find that C1 is getting charged to half of this input voltage, right? So here what happens is we are able to obtain a voltage level which is half of the input voltage. So what this is going to do is that it will increase the resolution of the output waveforms because you have reduced the size of the step, right? So the second state here, which I have shown, is the same one, like the output is 0 volts. If you follow this blue colored path, you see that the load is short circuited. This is basically to show the change in the direction of current, right? To show that this topology is working for an inductive load. Similarly, like if you see this um, state, here you see that we are using this capacitor C1 to obtain the load voltage, right? So in this case, like if you apply KVL, you see that the output voltage is 0.5 V in. So not only we are going to boost the input, but we are also at the same time we are able to reduce the step size here. So we'll see the advantage of this approach here. So if we analyze in a similar fashion, we'll see a number of states. Like here you are able to see the red colored path, which basically shows that both the capacitors are getting charged. Now in this state, you see that the capacitors are not getting charged, they are only in the discharge states. So here what is happening is V in is in series with C1, right? So the voltage of V in gets added to the voltage of C1, and that is equal to the output voltage. So this comes out to be equal to 1.5 times V in. Similarly, in this state, if you see, the voltage of capacitors C1 and C2, like it is in series with V in. So the output voltage is equal to V in plus VC1 plus VC2. So this comes out to be equal to approximately equal to 2 VDC, 2 V in. Right. So here again, like we are able to achieve a voltage gain of 2, and at the same time we are able to achieve a large number of voltage levels, because here 0.5 V in is also coming into picture. So if we these are for the negative states, and if we analyze this type of structure, these are the experimental waveforms, steady state waveforms here. So you see the input voltage was 100 volts, and we are able to achieve a peak voltage of 200 volts. At the same time, the size of the step, this size is equal to 50 volts, right? So what is happening is the overall number of levels here is 9. So that is a fairly good waveform. The harmonic profile is good, and it was tested for an inductive load. So that can be seen with the current waveform, that the lagging nature of this current can be seen here. Also, like I was talking about the balancing of the voltages of the capacitors. Here we have shown the two voltages, right, during the startup. So as soon as like you start this inverter, and as soon as this load current builds up, like the capacitors, they also get charged to uh, the predicted values of 50 volts each, right? So and they are like fairly maintained. These voltages are maintained even if like you carry out a sudden change in the sudden change in the load current itself. So here there is a sudden change, like the current is getting increased by almost twice. So 7 amperes peak value is like, here it is 15 amperes. So what we see that the voltages are like fairly maintained here, although the the voltage ripples, they have increased, which is expected, right? So despite like transients in the load side, we see that uh, the voltages of the capacitors are balanced at the expected values. Now coming to the currents, now that is important here, because the capacitors, they are coming in parallel with the source voltage. So here we see that some of the switches, they show asymmetry. For example, this current through a switch, like it achieve in the positive side, like this is a bidirectional switch, right? The diode, the anti-parallel diode is conducting in the negative side. So in one direction, the current goes to a peak value of 7 amperes, whereas in the other side, it goes to a peak value of 10 amperes. So this kind of asymmetry will be observed when we apply switched capacitor principle to multi-level inverters. But like you can appreciate, the two advantages are like very attractive, right? What are the two advantages? One is the voltage gain that we are able to achieve, and the other one is balancing of the capacitors. You don't need a closed loop system, you don't need sensors for the inverter part here. We also like implemented this topology for a three-phase system, and although it required three DC sources, I'll take one example where you can do so with a single DC source also. So the results are quite satisfactory, because the number of levels in the line voltage, so these are the line voltages. The relationship is very simple. The number of levels in the line voltages, that is equal to the number of levels in the phase minus 1. No, this is for the pole voltages. This is 2n plus 1, right? So if the phase has 9 levels, then here we'll get 19 levels. So in for the three-phase part, like the number of levels will be greatly increased. Now I am going to introduce one complex looking topology here. Here we are like looking to increase the voltage gain. Till now I discussed two topologies where the voltage gain was restricted to 2. So here we are going to increase the voltage gain to 3. We are also targeting to obtain a high resolution waveform. So the number of levels, like as I told you, like if the number of levels is around 11, 9 to 11, that then the inverter can be directly connected to the load without any filter. So here we are targeting an increased number of levels, and here like we get 13 levels in this topology, right? So I'll describe this topology. I'll take help of this structure to show how the components are to be designed, what are the main challenges, and how the control part of this structure is implemented. Now the control that I'm going to discuss is a universal control. Any kind of switched capacitors topology can be it can be modulated with the help of this scheme. And if any one of you like, if you're interested, I can share the Simulink models with you for all these three topologies. So what I have shown here is an analysis of the states, the way I was doing previously. So here you can see each state has two paths. One is colored in blue, which is basically for the load voltage, and the other one is colored in pink, which is basically the charging path for the capacitors. So this analysis is very easy here. If you see the states, like if I discuss this state, I am calling this state as sigma 1. This is just the name of the state. It has got nothing to do with like any other property. Here we see that the output voltage is 0, and you can track it by following this blue colored path. So what we are doing here is we are turning on these switches S1, S5, S8 and S12 simultaneously. And what happens is that the load gets short circuited here and the voltage across the load is 0. At the same time, like I have turned on this switch S4, S6 and S9. And what is happening here is this C1 is in parallel with VDC, input DC voltage, one thing, and a series connection of C2 and C3 is also in parallel with the source VDC. So here we see that C1 is in parallel with VDC, which means that it will get charged to a voltage equal to VDC, and C2 and C3, which are in series, that is in parallel with VDC, which means that both C2 and C3 will attain a voltage equal to 0.5 VDC each. Now, like based on the previous example, we know that this reduced voltage is important because it helps you in generating more number of levels, right? So in many states, like you see here also, wherever you see this pink colored path, you see that either C1 is getting charged or both C2 and C3 are getting charged by being in parallel with the input voltage VDC. There are certain states where these capacitors do not get charged. For example, this state sigma 5. Here we see that like we cannot charge these states because this original voltage VDC is in series with C1, right? So this series connection is supplying to the load, and as a result, the overall voltage across the load is 2 VDC. So in a in similar manner, like if we analyze each state, we see that we are able to achieve the peak value of the output voltage as 3 VDC, whereas the input was VDC. Moreover, the step size is 0.5 VDC, you see, 1.5 to 2, 2 VDC to 2.5 VDC, right? So step size is good here, 0.5 VDC. Similarly, like we can show the states for negative levels also, right? So what I have done here is I have named the states as sigma 1 to sigma 14, the total number of states here. The last state is used to obtain a voltage equal to minus 3 VDC across the load. Now, I'm going to discuss the approach using which we can modulate this kind of structure. This modulation is important because based on the modulation strategy, we design the capacitors, right? We have to, here I have not told you anything about the values of these capacitors C1, C2 and C3. So an important role will be played by in the way these capacitors are switching their states, right? Because in some of the states, the one capacitor, it is undergoing charging process, and in some other state it is undergoing discharging process. So it is important to analyze the modulation part also. So normally what happens in multi-level inverters is like we all know about the modulation strategy for a regular two-level inverter, right? In a regular two-level inverter, what we do is we take a carrier waveform, normally a triangular waveform of high frequency, and a sinusoidal waveform, which is the reference, and using this, we compare these two waveforms and we obtain the switching signals. This is what we do. So if you extend this kind of pulse width modulation, which is basically a sine triangle PWM, this can be directly extended to multi-level inverters also. All you need to do is you have to increase the number of carrier waveforms, right? So the general rule is like the number of carrier signals will be equal to number of levels minus 1, right? So here this is a two-level waveform. This is used for a two-level inverter, right? So 2 minus 1 is 1. So you need only one carrier signal. Now here, like we are targeting 13 levels. So normally we will need 12 carrier waveforms. So 12 is a very large number, right? So what this kind of modulation scheme that we are discussing here, it requires only half of it. Like you need only 6 carriers here. Okay, but the reference has to be changed. Like what we do here is we rectify the reference. Okay, so because all the 6 carriers are above the 0 axis line, so the reference also, like it is above the 0 axis, positive x-axis, so it is like rectified. We are using the absolute value of the reference. Okay, so if Vref is your reference waveform, then we are using absolute value of this reference waveform. Okay, now for each carrier signal, like if this amplitude is ACR, amplitude of the carrier, then we see that if we place each carrier on the top of the previous one, we see that this goes up to 6 ACR. And the peak value of the reference, this one, if it is AREF, then what I have shown here is this AREF is less than 6 ACR. So like basically I'm telling this because with the help of this figure, like we can define the modulation index in this context, right? So the modulation depth that we call is peak value of this reference waveform divided by this overall span in the y-axis that we see, which is equal to 6 ACR. So this is the modulation index for us. Also, what I have shown here is the states that should be used. Like for example, I have this carrier 1, and carrier 1 is being compared with this reference signal. So this is the like each carrier corresponds to one level, right? For example, this corresponds to 0.5 VDC. This corresponds to VDC. This corresponds to 1.5 VDC, and similarly we go up to 3 VDC. Okay, so here we understand that if the reference is compared here with the first carrier, then we get two levels here, and those two levels will be 0 and the lowest step, which is 0.5 VDC. Similarly, here also, when the comparison is made, again we should get two levels based on that comparison, and those two levels will be 0.5 VDC and VDC. Similarly, here VDC and 1.5 VDC, and so on. Right? For the top level, we will here, as a result of this comparison, we should get two levels, which are 3 VDC and 2.5 VDC. So what I have shown here is these yellow colored boxes. They show the states that should be implemented. For example, sigma 1 and sigma 2. So if you refer back to the description of states, here we see that sigma 1 gives you 0 volts and sigma 2 gives you 0.5 volts, right? Similarly, for the topmost part, we see that the states that should be enabled here should be sigma 6 and sigma 7. So here you see sigma 6 is 2.5 VDC and sigma 7 is 3 VDC. So that analysis of the topology is important when we actually implement the modulation strategy. Okay, so I have shown these yellow colored states. Now for the next half cycle, so this is for the positive half cycle of the reference signal. Then comes the negative half cycle, which we have like actually rectified. So for the remaining part, we should get the negative voltage levels, right? So I have shown those levels for each carrier signal, the comparison between each carrier and reference. I've shown those states which will give you the desired levels. For example, here for this part, we should get minus 3 VDC and minus 2.5 VDC. So the states which will be operated here will be sigma 13 and 14. So if you see here, sigma 13 is minus 2.5 VDC and sigma 14 is minus 3 VDC. Okay, so this is the description of the modulation index, the types of carrier signals that we are using, the reference signal we are using, and various states which will be implemented at each level. Now this analysis is important because as I told you, we are also discussing about the design of the capacitors. What value of the capacitor should be taken so that the inverter works satisfactorily. So the approach that we take for designing of the capacitors is called the worst case scenario approach. Right, so I'll discuss like what is the worst case scenario. So for the design of the capacitors, like normally for the switched capacitors topologies, we take the worst case scenario approach. So for this understanding this approach, like we have to go back to the states which we discussed. But before that, like we should understand like what will be the conditions which are imposed by the requirements at the output side, right? So normally when we are asked to design an inverter, we will be told about the output power. So this output power is known, right? Based on the output power, we can calculate the current, right? So output power divided by the voltage. So the output voltage that we get in terms of the input, as I told you, that we are able to achieve uh, a boosting of 3 here, right? So I have multiplied 3 with this VDC. Based on the modulation index, the overall voltage will be reduced. So M comes into picture here, modulation index. So the peak value uh, will be averaged to 3 MVDC, and the RMS will be obtained by dividing it with root 2, right? So here we know the RMS value of the current. So this is how we can calculate the RMS value of current. This calculation is important because based on this we'll design the switches, right? So let us discuss the worst case scenario here. So what I have done here is I have again shown the positive half cycle and the states which are to be used. Okay, now if you go back to the description of states, you see that like for the state sigma 5, the capacitors are not getting charged. For a state sigma 6, यहाँ पर there is no pink waveform, so none of the capacitors is getting charged. For the state sigma 7, where we are getting 3 VDC, here also the capacitors do not have opportunity to get charged. So what are the worst case scenarios? As I told you, for each carrier, like the inverter will operate between two levels, right? For example, it is operating between 0 and 0.5 VDC. So you have state sigma 1 and sigma 2 in picture. Now in both the states, the capacitors are having opportunity to get charged. So they are getting charged. So this is not any like, this is not a worst case thing. Here also when the converter is like, it is operating between the states sigma 2 and sigma 3. In both the states, like it is getting opportunity to, the capacitors are getting opportunity to get charged. Similar thing happens when it operates between sigma 3 and sigma 4. The only difference, like in sigma 4, this C2 and C3 do not have opportunity to get charged, but C1 gets repeatedly charged. Now, when the converter operates between these two states, this is a worst case scenario, because in sigma 5 state, the capacitors are not getting opportunity to charge. Sigma 6 also they are not getting charged. When they operate between sigma 6 and sigma 7, again they do not get charged, right? So here we should remember that for sigma 5, sigma 6 and sigma 7, the topology is not getting, the capacitors are not getting charged. So here you see sigma 6 and sigma 7, sigma 5 and sigma 6, right? So once the topology starts operating from this point to this point, which means that the voltage levels are like here, the voltage levels are 3 VDC and 2.5 VDC. Here the levels are 2.5 VDC and 2 VDC. So as soon as the output reaches 2 VDC, thereafter, like the capacitors do not have opportunity to get charged. Okay, so this is the worst case scenario between this angle theta 2 to this angle pi minus theta 2. During this whole time, all the capacitors C1, C2 and C3 are in discharging states. This discharging will cause ripples to appear in the capacitors, right? Also, we had talked about the current. Now the worst case scenario happens when the load is purely resistive, right? Why is this happening? So I'll take you back to the uh, state where I had shown currents for a different topology. I'll take some clean diagram. For example, this diagram. No, on this one. Okay, let us take this state. Okay, so if you see here, like the output voltage is obtained by a series connection of V in C1 and C2, right? Now the current is positive here and the current is negative here, which means that the load is either capacitive or inductive. It is not purely resistive. Okay. Now this state, when C1, C2 are coming in series with V in, it is like assume that in this state the capacitor will get discharged. Okay. And it happens actually. Here you see this is plus, this is minus, plus minus, and the capacitor is getting discharged when this current is negative. But when the current is positive, you see that the capacitor is actually getting charged. For the same state, based on the direction of current, the capacitor may get charged or discharged, right? But if the load is purely resistive and the current does not change its direction, then the capacitor will undergo only discharge process because there is no inductor to charge the capacitor in that specific state. So worst case scenario also happens when the load is purely resistive, right? So what we do is that based on this current and the given power, we design this for a purely resistive load because that is the worst case scenario for the capacitor. It will never undergo charging in a specific state unless it is directly connected to the source itself, right? The load will never charge it. So what we have done here is, you see, the amount of discharge that a capacitor goes through is dependent on the current and the duration. And this current is voltage divided by the resistance, right? Why we are considering only resistance? Because we are considering the worst case scenario. We are assuming that the load is resistive in nature, right? For designing, we are designing the converter for the worst case scenario. So the current flowing through it in this part, since the voltage is 2.5 and 2, right? So when the voltage is 2.5 volts VDC, then the current will be 2.5 VDC by RL. And when the voltage is 2 VDC, the current through the capacitor will be 2 VDC by RL. Okay, and in both the states, like the capacitor is undergoing discharge. So what we are doing is, for this whole duration, we are calculating the amount of discharge. Okay, so from theta 2 to theta 3, this duration, this is a PWM waveform, right? The waveform is PWM. That is why we have broken down this integral into a number of integrals with different limits. Okay, so from theta 2 to theta 3, there are two voltages, 2.5 to 2. Okay, but amongst these, what is the worst? 2.5 VDC is the worst. Why? Because the amount of current for a fixed resistive load, the amount of current will be large, which means that the capacitor will undergo more amount of discharge. So what I have done here is I have taken only 2.5 VDC. Similarly, from theta 3 to pi minus theta 3, which means this duration, the larger voltage is 3 VDC. So I have taken the current to be 3 VDC by RL. And similarly for the remaining part, like pi minus theta 3 to pi minus theta 2, I have taken the larger voltage, which is 2.5 VDC. Right? So these angles can be easily calculated, right? You know this expression like this, maybe this is Vm sine theta and this is theta 1, and you also know this magnitude, this is 4 CR. So based on like the modulation index, you can express these angles theta 2 and theta 3. You can express them in terms of the modulation index, right? So if you calculate this expression, it comes out to be like this. So the amount of discharge that it undergoes depends on the resistive load that we are considering and the actual values of these angles, which are dependent on the modulation index, right? So considering a 10% ripple, if you fit these values, 10% ripple means the capacitor C1 is expected to be VDC at voltage VDC, and I'm considering a 10% ripple, so that is 0.1 VDC. So if you consider that thing, then the value of C1 will come out to be like this. So we can see that it is dependent on the fundamental frequency. Important factor here, fundamental frequency jitni zyada hogi, the value of capacitor will be lesser, right? But since we are talking about renewable energy applications, fundamental frequency will be equal to the grid frequency here, 50 hertz. So that is fairly low frequency. But if you take other systems like an aircraft system where the fundamental frequency itself is 400 hertz, there the capacitor size will further reduce. So those are the very like attractive applications for this kinds of topologies. Okay, so the value of the capacitor is decided on the worst case scenario, and for that, like, you have to understand the overall states of the converter, the modulation scheme, and then you can actually calculate the value of the capacitor based on the worst case scenario. Similarly, like, similar analysis can be done for C1 and C2, and accordingly you can calculate the values of C1 and C2 also. Other ratings are easy to do. For the power switches, like, the main ratings will be the voltage rating and current rating. So based on the topology, like, the peak inverse voltage of each switch can be calculated. Once again, for this kind of calculation, you need to analyze each state. Okay, so I can give you an example. For example, I analyze this state sigma 12. So my approach is like this. This is how I do it. I am considering this point as my reference. So this is 0 volts. So which means that this is also 0 volts. S2 is on, which means that this potential is 0 volts. This will be plus VDC. And since S3 is on and this potential is plus VDC and C1 is charged to VDC, which means that this potential will be plus 2 VDC. So if you can, like, find out the potential at each junction, then you can see the potential difference across all the switches which are off. For example, switch S1. One point the potential is 0, other point the potential is 2 VDC, which means that for this specific state, the voltage stress which is being borne by S1 is 2 VDC. So what we have to do is, for all the states, we have to see the voltage stress across switch S1, and the maximum of that voltage stress is taken as the peak inverse voltage. Another easier method is, like, you simulate this topology with 100 volt DC and you see the voltage waveform across, like, a switch. So whenever the switch is off, a voltage will appear across the switch, and that peak voltage will give you an idea of the maximum voltage stress that it has to bear, right? So what we do is we carry out this kind of analysis and we determine the maximum value of that voltage, right? We call it PIV, peak inverse voltage. So as I analyze, like, for S1, the peak voltage comes out to be 2 VDC. So for each switch here, I have shown the maximum voltage that it has to bear. Okay, but we should remember that the output voltage has a peak value of 3 VDC. And you are able to obtain this value by employing switches with with much less voltage rating. So this is the fundamental advantage of a multi-level inverter. We are using low voltage rated switches to obtain a high voltage, right? So this is how we will get the voltage ratings of the switches. Current ratings, like, it is a bit tricky in these kinds of topologies. Normally, like, the load current is equal to the maximum load current is equal to the maximum current rating of the switches. But here what we are doing is we are also using the switches to charge the capacitors, right, with the help of the load source. So for example, whenever this capacitor C1 gets charged, you have to turn on this switch S4. Okay, so what happens here is C1 is in parallel with VDC, considering D and S4 to be ideal, but they are not ideal. So in this type of like equivalent circuit, we can calculate the current. This is a simple RC circuit. R will come into picture due to the on-state resistance of the diode and the switch S4, right? There will also be the voltages here, the diode voltage, the voltage of the capacitor C1, which is ideally it should reach to VDC, and in that case, this part will become 0, and the equivalent like series resistance of the capacitors, which is like incidentally, like this is a factor which helps us here because it will limit the charging current. Okay, so now this charging current is exponential, but overall resistance is less, so the time constant of the circuit is very less, so it quickly gets charged to the desired voltage. Okay, but here like the maximum value of this current is important. Similarly, whenever like the series combination of C2 and C3 comes in parallel with VDC, again like we can calculate this current. Again, this is an RC circuit and we can calculate this current. Okay, so based on these calculations, like we can calculate the current stress in different power switches. Now this is important here. Some of the switches, they have to bear only the load current, but there are some of the switches which have to bear the load current, charging current of the first capacitor and charging currents of the second and third capacitors, right? For this again, like we can go back to the switching states. मैंने कचरा कर दिया diagrams, but here like you can see ये जो diode है, it is bearing this charging current, right, of C1 as well as C2 and C3. Whole of that current is flowing through this diode. If you move to state S3, this sigma 3, this diode bears not only this pink current, which is charging current of both the capacitors, it is also bearing this blue current also, which is the load current. So the diode should be able to bear this current stress. Okay, so this is how by the analysis of each state, we can analyze the maximum value of current that a switch has to bear. Okay, so this is the load current, charging current of first capacitor, charging current of capacitor 2 and capacitor 3. So this diode is to be rated at a very high current value. Okay, so for all the components of this circuit, I have described like how to design the capacitors, how to determine the voltage and current ratings of the switches. Okay, so based on this, like we can draw a general approach to design this kind of converter, right? So it always starts with the output side specifications. I am assuming that for a renewable energy application, like you have a flexibility in determining like coming up with a DC voltage, right? You have panels, so you can do some kind of series parallel combination to achieve a certain DC level. So based on the output side specifications, which are the power and the RMS AC, you can determine the input DC, right? So 3 is the boosting factor here. M is the modulation index. So based on that, you can determine the input DC voltage which will be needed. Now, once you have determined this input DC voltage, you can find out the voltage ratings of the power switches. Okay, and accordingly, like you can find out the voltage ratings of the capacitors also, right? C1 gets charged to VDC, so it has to be rated minimally at VDC. C2, C3 are charged to voltage 0.5 VDC, so they are to be minimally rated at 0.5 VDC. Then we can determine the values of C1, C2 and C3 using the equations. I have not shown the equations which we had discussed, right? And we can determine the current ratings of the power switches. So this is how the approach to design a switched capacitor topology in general, this kind of approach can be taken. So this way, like if we design this structure, I have shown some experimental results here. So this current is around 6 ampere peak value, and uh, this voltage, like you can see, it has 13 levels here. Main concern here for us is the voltages of the three capacitors. So we are able to control the voltages of the three capacitors to like maximum of a 10% of ripple. Okay, because they were designed that way. If you see the dynamic response, like if the current is increased suddenly, naturally there will be increase in the capacitor ripples, but the overall like voltage waveform is satisfactory. One interesting thing happens here is, like, even if you decrease the modulation index, here the modulation index is very high, 0.95 to 0.9 somewhere. Here the modulation index is very low. So as you decrease the modulation index, the number of levels will get reduced. Modulation index is reduced to such a level that a manner that the output voltage has only 3 levels. Still, the capacitor voltages, like they are maintained at the specified value. So this is important here. So it is natural because you are bringing the capacitors in parallel with the source. This is a very interesting topology that I have shown. I have also shown the reference. Again, this is a 13 level topology, but the voltage gain here is very high. Right, so here they have used a very interesting approach, like what I was telling you, that you have to bring the capacitor in series in parallel with the source. Okay, and at times what I did is I brought a series connection of C1 and C2 in parallel with the source. So basically the capacitors were charged to 0.5 VDC. Now what these researchers are doing, they are doing just the opposite thing. They are bringing the series connection of the voltage source, the capacitor, in parallel with another capacitor. Okay, so I'll show you. What we did is we brought this capacitor in parallel with this source. Let us say we have one more capacitor. So what we did is we brought all three of them in parallel. Now in this work, what they are suggesting is you bring this capacitor C1 in parallel with the source. Okay, so this C1 will get charged to a value VDC. Now for C2, you take this series connection of VDC and capacitor. This is VDC, this is capacitor C1. You take this series connection and you bring it in parallel with C2. So C1 was charged to a voltage VDC, which means that C2 will be charged to a voltage 2 VDC. So you can further improve the boosting part without adding additional capacitors. Okay, so what these people are doing here, they have a voltage source of VDC. They are bringing C2 and C1 in parallel with the source so that these capacitors are getting charged to VDC. And now they are bringing series connection of VDC, C1 and C2 with C4. So C4 gets charged to 3 VDC. Similarly, C3 also gets charged to 3 VDC, which means that the output voltage, it goes up to 6 VDC. Okay, so from VDC, like you are boosting the voltage to 6 VDC. So this is another approach. We call it asymmetric charging. You're not charging all the capacitors by bringing them in parallel with the source itself. Rather, you are taking help of other capacitors to charge like one of the capacitors. Okay, so this is And asymmetric charging, uh, very interesting work. The only disadvantage of this work is like if you decrease the modulation index, the capacitors will not get charged to satisfactory levels. This is the only disadvantage. So for high power factor load, the value of capacitor will be very large. Only disadvantage of this. So like this, like I gave you example of 4 different topologies. If you have a look at the literature, there are at least 50 different topologies, right? So how to compare those topologies? It is actually like in literature, it is actually recorded that they can be compared based on one factor which we call as the cost function. This one factor which can quantify different features of a switched capacitor topology, and we can compare based on this cost factor the performance of various topologies. It is very simple, like uh, just you have to see the boost factor. What is the boosting? Like for example, the topology that I just showed has a boosting factor of 6, right? You have to see the number of sources required. All the topologies that I showed have require only one source. There are different topologies which require multiple sources also. You have to see the number of levels that it is able to generate, and this is all about the number of components. Okay, so number of switches, number of diodes, number of auxiliary diodes, number of gate drivers, and number of switches. Alpha is just a weighing factor. This TSV is total standing voltage, which means addition of voltage stress of all the switches. Okay, basically this determines the cost, right? The more is TSV, the more will be the cost of your converter. Components, they determine the cost as well as volume of the topology. So less is the cost function, better is the topology, right? So this is a small like description of um, these components. Of course, as I told you, asymmetric balancing, what is it does is that if you reduce the modulation index, then you may not be able to charge the capacitors to the desired values. So we can classify these converters based on the number of stages in two-stage topologies. Like we have an H bridge, due to which the voltage stress increases actually. Single stage topologies, the voltage stresses are less, but the number of switches is normally more. So symmetric charging and asymmetric charging is another way you can classify these topologies. I have described it. So for the structure that I was discussing, like here I have shown the waveforms of currents also. So this is a 13 level output of the topology that I was showing. Here you see this current across the load, the current through the load is around 6 amperes. But for some of the switches, you see the current touches a value of 20 amperes also. So these are the spikes which are coming in the switches when the capacitors become in parallel with the source, right? So this is an important limitation of these topologies. The spikes that are encountered, the current stress in various switches will be more than the load current itself. So as I was talking about the typical applications like high frequency distribution, as I told you, like the capacitor size is inversely proportional to the fundamental frequency here. So high frequency AC distribution in these kinds of systems, like we are using high frequency as the fundamental waveform. So these converters are highly attractive, especially for the microgrids, for small grids, buildings, for electric vehicles, like where we can use high frequency AC distribution. PV-based power generation system, once again, an extremely important application because most like the PV arrays, they generate very low voltage levels, and the boosting that is to be done can be done in various ways, right? One way is to obtain a high voltage string by connecting number of like PV panels in series. But we know that this kind of connection, like it gives rise to mismatch issues. Okay. Other ways to achieve boosting is either to do the boosting at the DC to DC side or in the AC side. Okay, so you can add a DC to DC boost converter at the front end. But then again, this approach will become a two-stage approach. You have to do DC to DC conversion and then DC to AC inversion. Okay, so that will add to the cost, the volume, and the power losses. Another approach, like you can obtain a low voltage AC and you can step it up with the help of transformer. But once again, like associated costs will be more and power losses will be more. Okay. So when we use a switched capacitor MLI, it offers many advantages in this kind of system because the inherent voltage boost will lead to reduction in this boosting requirement. Capacitors are self-balanced, so you do not need a complex control scheme, an expensive an expensive system where you need a lot of sensors and processing requirements. If the voltage waveform resolution is high, then the filtering requirements will be greatly reduced, and in some cases, like they may be even eliminated, so you can directly connect it to the grid itself. Okay. Many researchers have demonstrated the application of the switched capacitors inverters to electric vehicle traction systems, to three-phase motors, to even to five-phase motors also. So here also, like these systems, we use two types of configuration. You can take the battery pack and you can directly connect it to the two-level inverter. But in this case, like you need to have a good high voltage, high DC link voltage, right? So what you have to do is like you have to make a series connection of the batteries. Okay, and this is actually problematic because the equalization of charge is challenging in series connection. And if there is any fault in any cell, then you have to dismantle the whole like string to repair it. Another approach is, of course, is to have a series parallel combination and then use a DC to DC boost stage. Once again, like it is a mobile system and you want to have the system to be you want to have it very compact and reliable, right? So this DC to DC boost stage does not actually help in that. So SCMLI is like their viable interface because one very important additional advantage is like basically what you're doing is you are controlling the speed of the motor with the help of the reference signal, and if the speed is high, then the frequency of your reference signal is very large, right? And to obtain like a satisfactory waveform, the switching frequency has to be more than the reference signal itself. So in these cases, like when you are using multi-level inverter, where the voltage rating of the switches is much less as compared to the output voltage, what you can do is that you can use low voltage devices, that is MOSFETs, which can operate at very high frequency. So the speed control becomes very reliable there. Okay, so this is a very important advantage. So this is all from my side. If there are any questions, comments, like they are welcome.
Okay. Participants.
I hope people are like awake.
Hello.
Yeah.
हेलो गुप्ता सर.
हाँ जी सर.
यस सर. सर मेरा एक ऐसा सवाल था कि अभी if we are working on a wind turbine, so if a small micro wind turbines, And at a lower wind velocities, we want to charge the 12 volt battery. And at higher wind velocities, we want to switch it to the 24 volt battery charging, sir. So is there any devices which are available so that they can switch from 12 volt charging to 24 volt charging based on the wind velocity for micro wind turbines?
You are using
because I want to keep the ampere rating constant, sir. Current rating constant, because that is the winding limitations. So voltage I want to switch it to 12 volt charging to 24 depending on the increase in wind velocity, sir.
Okay, you're using your wind system to charge batteries.
Yes, sir. Yes, sir.
Okay. I'm not able to think of.
Because now what happening, sir? If I connect directly to 24 volt charging, then at lower wind velocities I am unable to charge the batteries, and at higher wind velocities ampere rating is increasing and windings are getting heated, sir.
Right. But you are like directly connecting the output to the battery, like you are rectifying it also, right?
Yes, sir. I'm three phase to DC. I'm converting through the rectification, and then I am using the buck converters for the maintaining the constant voltage for feeding to the battery, sir.
Okay. See, part of, I don't know, probably the solution that I am telling you is very like complicated solution, but
Yes.
like in electric vehicle applications, charging of like charging stations, like the requirement of the DC, normally we do it with two stages, right? AC to DC and DC to DC stage.
Yes,
DC
sir.
to DC stage, like basically for isolation part we are using. In the AC to DC stage, one important requirement is wide output range.
Wide
Okay,
output. Yes, sir.
the output range of that controlled DC has to be very wide. So we are doing one interesting work. See, I told you about the switched capacitors multi-level inverter, and what is happening there is you are converting DC to AC, and
Higher
the
voltage.
voltage is getting boosted. Okay.
Yes, sir. Yes,
If
sir.
you perform the reverse part,
Yes, sir.
what happens is that you convert AC to DC and the voltage actually gets bugged. Okay, it gets reduced.
Okay, sir.
And like here, like if the voltage is like the voltage gain is 3 for the inverter side, then actually the voltage reduction factor is like 1 by 3 there. So one of my students is working on charging station, and he has used a switched capacitors topology to change the voltage range. Like the range is very large actually. So probably like you can use a system like
Yes.
instead of having a diode rectifier,
Yes.
you can use a fully controlled rectifier where you can change the voltage output voltage level based on the using the rectifier and based on the speed of the wind. I don't know, probably it should help you. Like the
Sir,
only requirement, the only requirement will be the range of voltage. You know, you want to come down to 12 from 24. So the rectifier topology should be such that it should offer that kind of flexibility. So probably the switched capacitor based AC to DC converter, you won't find like a lot of literature there. Probably there is only one paper by Irwin or some author where they have proposed a three-phase system like this. But for charging infrastructure, you'll get many papers like
so
this.
basically, the thing is that I am a mechanical domain.
Okay,
So
okay.
I'm searching for anything which is readily available for its kind of for performance study and all.
Okay.
Yes, sir.
What is the voltage output that you're getting from your wind power system?
Yes, sir. Wind power system, we are working from up to 3 meter per second to 10 meter per second, sir. And the wind, with respect to the wind velocity, from 8 volts to 63, 64 volts, like that, it is varying, sir.
So probably you should use a buck boost. Bhupen sir, can you comment on this? A normal buck boost converter should help you because the voltage.
Yes, sir. I am working on buck converter only, sir. I used buck converter only. I have tuned the buck converter in such a way that it can feed to the 12 volt battery. I kept a 14.5 volt as the maximum limit to charge a lead acid battery, sir. 12 volt lead acid battery. But for higher wind velocities, I don't want the current to change. I want voltage to increase to 24 volts, sir, automatically.
Automatically it will happen, like the duty ratio will be changed,
Yes.
but the current will also change there. So then the solution will be like a controlled converter and your buck converter
Okay. Yes.
instead
I
of
think
a
that
diode rectifier.
the control algorithm will be a quite complex one with closed loop control, something like a thing, I feel.
Yes, sir. Yes, sir.
That means controlling the DC output of the control rectifier as well as the duty ratio of our this thing, DC to DC converter.
Yes, sir.
So, you have your DC to DC here, and this is the input DC, and this is the output DC. So, what is happening? Like, you want to keep this current as constant, right? You don't want to change the magnitude of this current,
Yes, sir.
and the voltage goes up, which means that the power actually goes up,
Yes, sir.
and accordingly, like changes will be seen in the load side also. So what I am telling you, like here, instead of diode rectifier, you use a regular like fully controlled converter, AC to DC converter,
Okay,
and
sir.
this is your AC source,
Yes, sir.
basically which has the amplitude is changing, right?
Yes,
So
sir.
a simple PWM control of this will help you in managing this voltage.
Okay, sir.
This is my take. I don't know amongst the participants, uh, probably someone knows a better approach to solve this problem. लेकिन अगर आप दोनों स्टेजेस में सर अगर आप कंट्रोल्ड कन्वर्टर्स यूज करेंगे तो आपके पास बहुत फ्लेक्सिबिलिटी रहेगी.
Okay, sir.
और अगर आप इलेक्ट्रिकल फील्ड के हैं भी नहीं, अगर आप एक रेगुलर आपका ये विंड टर्बाइन 3 फेज आउटपुट दे रहा है, राइट?
Yes, sir. Yes, sir. Three-phase output there, sir.
आपको नॉर्मली आपको बहुत सारे यूट्यूब चैनल्स में वो बता देंगे कि एक 3 फेज कंट्रोल रेक्टिफायर के लिए कैसी कंट्रोल स्कीम होनी चाहिए. अगर आप दोनों स्टेजेस को कंट्रोल कर रहे हैं तो आपका जो ऑब्जेक्टिव है वो पूरा हो जाएगा.
Okay, sir. Okay,
That
sir.
is my
Yes, sir. With this input, I'll check into that, sir.
sure.
Thank you, sir. Thank you, sir.
Thank you.
Okay, the participants here are many multidisciplinary type, electrical,
Okay.
mechanical. Yeah.
ओके ओके आई एम सॉरी, मैंने बहुत ज्यादा फिर कन्वर्टर पे बहुत ज्यादा मैंने वो कर दिया.
No,
सो सॉरी.
at the time of introduction, even I have told you that a little bit of biasing towards electrical side will be found in this course as it is conducted by electrical engineering department, and we have given more stress to power electronic interface and all control. But it is a part, and
और इट इज नॉट जस्ट अ पार्ट सर. एक इम्पॉर्टेंट चीज ये भी है कि आप कोई भी रिन्यूएबल एनर्जी सिस्टम देख लें, उसमें जो वीकेस्ट लिंक है वो पावर कन्वर्टर वाला ही पार्ट है. तो वी हैव टू बी गुड इन दैट. मतलब वो आप देखिए कोई भी फोटोवोल्टाइक सिस्टम है, पैनल्स की वारंटी 25 साल है, लेकिन कन्वर्टर की वारंटी, इन्वर्टर जो कि उसकी वारंटी 10 साल है सर. सो उसमें जो इनपुट देना है वो तो हमें बहुत सीरियस इनपुट देना ही पड़ेगा, तभी हमें एक अच्छा रिलायबल सिस्टम मिलेगा. अदरवाइज इट इज वेरी डिफिकल्ट.
participants, more questions from electrical side? Any more questions? So I hope we are done with it. So I formally conclude this session. I express my sincere thanks to Professor P.K. Gupta sir, giving such a wonderful presentation on the design of multi-level inverters, especially the switch capacitor topology. It was my fortune that we have worked together in the same lab for our PhD duration. And I know Mr. P.K. Gupta that he is a master of hardware, especially power electronics hardware. He has a good exposure to design of these hardware using DSpace, DSP controllers. We look forward to you, sir, for further such information.
Yeah, I am thankful to you, sir, for giving me this opportunity. Thank you so much.
Thank you, Dr. KK. Very much. Can we share this presentation with the participants?
Yes, sir. Yes, sir. Yes, sir. And in case like